Welcome back, everybody. So today we're going to look at infinite geometric series and mathematical induction. So we'll start with the infinite geometric series. So up at the top, we've got just a little reminder from last time. If we have a finite number of terms, we can calculate the sum of the series by using this formula on the right. And we derived that from the previous notes. So today what we're going to look at with geometric series is, suppose that we don't have an ending term. We're just going to continually add up more and more terms. So what does that mean for its sum, right? So does the sum exist, or is the sum just some form of infinity? So to start, we're going to look at two particular sequences. So we've got them written here. So we have the sequence on top is 1, 3/2, 9/4, 27/8. So take a moment to convince yourself that that's a geometric series. And just below that is another series or sequence, which is 1, 1/2, 1/4, 1/8, and so on. And go ahead and convince yourself that that's a geometric series. So if we look at both of these and we start adding up terms, what are we going to end up with? So if we go to a separate page here, we can kind of look term by term by term. And what we're going to be interested in is those partial sums, right? So what is the sum as I start adding up each set of terms? We'll note that the infinite series that we're describing is simply 3/2 to the n minus 1. So the sequence is 3/2 to the n minus 1, and we're adding up each term as n increases. So for s sub 1, clearly it's just going to be 1. The sum of the first two terms is going to be 1 plus 3/2, which is going to be 2.5. The sum of the first three terms is going to be 1 plus 3/2 plus 9/4, which is going to be 4.75. And if we added 27/8, let's actually see what that would be. So 4.75 plus 27/8, and that gives me 8.125. Okay, so clearly if we're looking at these first four terms, it looks like our sum is getting bigger, and it looks like it's getting bigger faster, right? So from term 1 to term 2, it's increasing by 1.5, and then it's increasing by more than 2, and then it's increasing by more than that afterwards. So clearly we can see it's getting bigger, and there's no reason to believe that it's going to be getting any smaller, which means if this is continually getting bigger, what would we say is the sum, right? So it looks like we would say that the sum is equal to infinity, right? But what does that mean? Right, so what does it mean to be infinity? So let's go ahead and jump over to Desmos. So we've got our geometric sequence here, and note this is going to be the function version of it, so the exponential function. And we can see that 3/2 to the x minus 1 is an exponential growth function. And if we look at the right of that curve, it is heading straight up almost. Right before we get to 10 even, you can't even see it on the page anymore. So clearly these terms are just getting bigger and bigger and bigger. So if I were to take that summation formula that we derived last time, which is in that third box here on the left with capital S, then if I graph the sum formula, it's also getting bigger and bigger and bigger. So this is a sum that is going to be approaching infinity. So for that first series, as n goes to infinity, so does the sum of the series. So we say that this series diverges. And diverges is just another way of saying that the sum is going to increase without bound. It's going to approach some form of infinity. It could be going to negative infinity as well if we had all negative terms. But diverges means there is no sum value that we can set to this particular sequence when we add up the terms of it. Okay. So let's go back to then our second series, which is similar, right? The first term is 1, but now we're adding the next terms, which are going to be found by multiplying by 1/2 instead of 3/2. So we can look at our sequence of partial sums. So S sub 1 is 1. S sub 2 is 1.5. S sub 3 is going to be 1.5 plus a quarter, which is going to be 1.75. And then S sub 4 is 1 plus a half plus a fourth plus an eighth, which is going to be 1.825, I believe. Let's check that. .75 plus 1 divided by 8 is 1.875. It's off by a digit there. Okay, so 1.875. So now, if we look at this first 4 terms, clearly we don't have the same rate of increase, right? So my value is getting bigger, but it's getting bigger at a slower rate, because from S sub 1 to S sub 2, it increased by a half. S sub 3, of course, it increased by a fourth. So we can see that the value we're adding, which is clear in our series, is a smaller and smaller value. So we're adding a smaller and smaller number each time. So our sum then seems reasonable that it might exist if I'm adding smaller and smaller values. So let's go to Desmos. And if we look at the graph for that exponential curve, we can see it's decay, right? So it's decaying, so clearly the terms are getting smaller and smaller and smaller as we increase the value of n. So if I look at the summation as a function of that particular sequence, it looks like, let's zoom out a bit here, it's like we're leveling off, right? So if we zoom in a bit, what value are we leveling off to? It looks like y equals 2. So let's compare y equals 2, and you can see that that purple curve just completely disappears. So our sum as a function is approaching 2. And if we look at our sequence of terms, it is also approaching 2. So then our sum, just in general, is equal to 2. But that kind of raises the question, does it ever actually equal 2? Right? Will there be a point where I have S sub 1,000 equals 2? No. So what we get is a value that is closer and closer to 2. And in fact, we can get as close as we want. So if I wanted to, I could find a particular value that gives me a certain number of 9s after the 1. Right? So I could find some particular n that's equal to 1.9999. We can get as close as we want to by adding more and more terms. So the way we would describe it here is that as n goes to infinity, s is going to equal a number. In this case, it's equal to 2. But in general, it's going to equal some numerical value. So the sum is going to approach a numerical value. We say this series converges to 2. So we have two terms here that are going to be very important for infinite series: divergence and convergence. So if we diverge, we're approaching infinity. If we converge, we're approaching a numerical value. Now the question is, how do I actually get the sum? Right? So how do I actually calculate that sum without, going through that partial sum process? So if we look up at the top at our summation formula, we're actually going to use that formula and we're going to simplify it in a way. And we'll note that for these two series, what's the key difference between them? Right? What is the difference that makes it diverge versus converge? So for our first series, if we think of it in its function form, this is exponential growth. If we look at the second series, this is exponential decay. And that's the key, is that if we have a decaying function, it's going to shrink to a specific value. And if we have a growth function, it's going to expand to infinity. Now, this is going to only be true, though, for geometric series. We can have other series that seemingly decay that can approach infinity. But for exponential, if it's growth or decay, that is going to be a direct correspondence to divergence and convergence. So that's growth, and convergence, going to be decay. So how do I tell if a exponential model is growing or decaying? I look at the rate. And so we'll note that decay means that R, and we'll say the absolute value since we can have negative numbers, is less than 1. So we're going to have to guarantee that to be true in order for our convergence to occur. So for our definition here of the sum of an infinite geometric series, we have to add the caveat if the absolute value of the common ratio is less than 1. And the sum is going to equal something very interesting. It's going to equal the first term divided by 1 minus r. If we go up, we can see that that's almost this first formula. But it's not this first formula because it's missing something, right? 1 minus r to the n. So where did that go? Well, let's just note if r is less than 1, then r to the n approaches what value as n goes to infinity? Okay, so imagine we have 1/2 in there for r. Right? As n approaches infinity, what is 1 over 2 to the nth power going to go to? Take a moment and think about it. All right, well, if this is getting smaller and smaller as n increases, then it's going to 0. Right, so that r to the n goes to 0, which means the top just becomes 1 minus 0, which means we're left with just a sub 1 over 1 minus r, because that 1 minus r to the n is 0. So that is going to give us the sum form of our infinite geometric series. And now our key step then is figuring out the common ratio. So we'll do these first two examples here. So we want to find the sum of these two geometric series. So we'll start with just checking the common ratio between them. So for the first example, we've got r is equal to 2/3, which is clearly less than 1. Thus, series converges. And we should also note a sub 1 is equal to 5. So then our sum is equal to 5 over 1 minus 2/3. And now we just need to do a little bit of algebra. So we get 5 over 1/3, which is the same as 5 times 3 over 1, which is 15. So if we start adding up terms of this series, 5 times 2/3 to the k minus 1, it's going to start approaching the number 15. So our series converges to 15. All right, so then for the second example, r is equal to 3/2, which is greater than 1. Thus, well, if it's greater than 1, it's a growth function. So the series diverges. And we have no sum. So no sum exists. So that's going to be the key for a lot of these examples, is figuring out, does it converge or diverge first, and then appropriately calculating. All right, so we'll scroll down here to that second page. We'll do these examples next time, but I would say go ahead and try them on your own first, and I will see you then. So take care.